All right, here we are starting chapter 2. We're going to start off identifying the location in a distribution, something called the percentiles and z-scores. I'm sure you've already heard about percentiles. Um, so on a test, a student's percentile isn't the same as the percent correct. So if somebody gets a 70% on the test, does that mean they're in the 70th percentile? No. It just means that 70% of the students that took the test did worse than you. So if you are in the 20th percentile, then 20% of test takers did worse than you. If you're in the 50th percentile, you're right there at the center, and half did worse than you. I crossed off the 100th percentile being the highest value. There's a little school of thought on this. Some people do say at or below a certain score. I think we just go with below a certain score. So in that case, you never really could be the 100th percentile, but you could be in the top 99.99999 percentile, which means if you scored the absolute best, you don't have 100% below you because you're still counting yourself. So a percentile is not a score, it's just the position that one score is relative to everyone else's score. So we're looking at wins in Major League Baseball. So this stem plot shows there's 30 Major League Baseball teams, so I know that there's 30 numbers in my stem plot. We want to calculate and interpret the Colorado Rockies, who had a 92. So right here, I'm going to go here and find where the Rockies are. So I could count all the ones below, or I could more easily count the ones above. So 1, 2, 3, 4, 5, 6. So if I do 30 minus 6, so for the Rockies, 24 out of 30 scored lower. So 24 out of 30 is 0.8, so the Colorado Rockies are the 80th percentile, which means 80% of the teams so 80% of the teams had fewer wins than the Rockies. Okay, the Yankees. And so this is 2009. The Yankees did really well. So the Yankees had 103. There they are. So the Yankees. So again, we're not going to get the 100th percentile because I want to know how many did worse than the Yankees. And that's 29 out of 30. So 29 out of 30 is 0.97 almost. You get some decimal, but percentiles must be whole numbers. So they're at the 97th percentile, which means 97% of the teams had fewer wins. So ... And then we've got the Cleveland Indians, where I'm not from Cleveland, but I rooted for either the Reds or the Indians. So the Indians didn't have a great year, so they're here at 65. Now notice there's a couple 65s. So again, I don't know which one they are, but again, it's about how many did below them. So with the Indians, only 3 teams did worse. So they would be at the 10th percentile. So again, only 10% of the teams had fewer wins. So again, percentiles have to be whole numbers. So I shouldn't say the 99.999, I should just say the 99th percentile up there. But in our AP class, this is what we're going to use. So percentiles are the percentage that have scores lower. Okay, so how can we use, this is a cumulative frequency chart, meaning that we keep adding up the percentages as we go until we reach, this would be 100%, 0%. So we just continually add percentages together until we get all of them at 100%. Okay, so this is showing the distribution of median household incomes for the 50 states and the District of Columbia. So it says California with a median household of 57, what is this from? Where the household income is 57,000 is at what percentile? So what do? I estimate where, this is the income on the bottom, that's why it's important to label so I know what to look at. So 57, that's almost 57,500, so it's about right there. So California, that 57,000 number is right there. What do? I go straight up, pretty straight up until I hit my line, and then I go over. Did I go down a little bit? Okay. So if you have a straight edge, that can be helpful there. So I'm right below, I'm between the 0.7 and the 0.8, so I might say that they are the 75th percentile, because that's where they are. If I look right there, I'm estimating where they are, 75th percentile. And again, when it says interpret this value, it means 75% of the states had median incomes less than California. Median income. So again, that's always in context. So 75% of the states had median incomes less than California's median income. Okay, then I could ask you, what is the 25th percentile for this distribution? So instead of starting here with that given household income, I'm now going to go over to the, where's 25%? So again, 20, 30, so 25% would be about right there. So again, I'm just going to go over horizontally until I hit the graph, and then I'm going to go straight down, and it looks like I hit about 45,000. So notice the 25th percentile. This is also your quartile 1. So if you're at the 50th percentile, you're at the median. If you're at the 75th percentile, you're at quartile 3. The 25th, so another name for this value is quartile 1, or the first quartile. So what is the 25th percentile? It is approximately a median income of about 45,000. Okay, where is the graph the steepest, and what does that indicate about this distribution? So I'm going to go with, and again, it doesn't have to be a dot to dot because that looks about the same. In fact, that's not even much. I might say, where is the graph the steepest? So I'd say the graph is the steepest from about 40,000 to about 55. So from 45, or I'm sorry, from about 40 to 55. And if I look at where that is, again, that is not quite at 0, so the difference between this and this is probably about 70%. So about 70% of the states and DC, shouldn't forget about them, have median incomes between $40,000 and $55,000. Okay, so those are what percentiles are. Okay, so something we're going to talk about a lot this year are z-scores. They're called a standardized score that we'll use on the normal curve. So how do you calculate and interpret a standardized z-score? And do z-scores have units? No. So we don't talk about inches. It's just a standardized unit. And what does the sign of the standardized score tell you? So if you have a positive z-score, it means you are above that mean, because again, the mean is the center, and a negative z-score is below. So this is from your textbook. So if X has an observation that has a known mean and standard deviation, how we find our z-scores, we take our individual point that we're given, minus the mean, and divide it by the standard deviation. So this is called a z-score. We're going to use these for proportions. I'm going to not talk about a proportion today, but later on we'll do something called a t-score. So this is where z-scores come in to let you again compare. So Macy, she's 3 years old. She's a female, 100 centimeters tall. Brody is her brother. He's 12 years old. He's 158 centimeters tall. Obviously, Brody is taller than Macy, but who is taller relatively speaking? So that is other kids of the same age. Who is taller? So according to the CDC, the heights of 3-year-old females have a mean of 94.5 and a standard deviation of 4. So to find the z-score for Macy, I would take her height, that's our X, is her individual height, minus the mean that they say is true of everybody. So I'm going to take 100 minus 94.5, and I'm going to divide it by her standard deviation of 4. So that gives us 1.375. So Macy is 1.3 standard deviations above the mean. That means she is taller than other females her age. And then the z-score for Brody. Brody is 158 inches tall, but what do they say is the mean height for 12-year-old males? It's 149. Again, he's taller than average, standard deviation of 8. So with Brody, we're only going to get a z-score of 1.125. So they are both above average height, but compared to children and genders their own age, Macy is actually taller for her height. So Macy is more above average than Brody. They're both above average, but she is more above average than her brother. Okay, so there's the math we're doing. Hopefully not too difficult. Okay, so let's look at baseball players and home run kings. So we've got some famous players that are known for hitting what is considered above average home runs. We got in 1927, we have Babe Ruth. So what we're given is we're given the home runs that they actually had in that given year, what the mean number of home runs were for the entire league, and what the standard deviation was. So again, who is the better? Who had the better home run hit? So if I just look at this, it looks like Barry Bonds because he had the most. So if I just look at this, it looks like Barry Bonds would be the home run king. But if I find the z-score for each, so if I find the z-score for Babe Ruth, I'm going to take his mean minus the mean of the entire league and divide it by the standard deviation that year. So if I do my math correctly, 5.44 standard deviations above the mean. If I do Roger Maris, who's next, so if I do the z-score of Roger Maris, with that one, we're doing his number of home runs minus the league average that year divided by the standard deviation, 3.15. Again, we kind of talked in class a little bit about if you're more than 2 standard deviations away from the mean, you are an outlier. So Babe Ruth, though, is definitely further along to the right than Roger Maris. But again, that's still way above average, but it's more than 3 standard deviations. Then we have Mark McGwire. So 70 minus 20.7 divided by 12.7. 3.00. I'm looking at a paper that I already have done, and I can't tell if my math is right there. It looks, one of those might be 8. You double check me. And then Barry Bonds would be our 73 minus 21.4 divided by 13.2, and that is 3.91. So calculate the standard and compare. Definitely Babe Ruth. So all 4 players were more than 3 standard deviations above the mean, which is phenomenal. Good, notice I can abbreviate standard deviation, just SD. It looks like Babe Ruth was the best. Okay, so asking you to interpret. So in 2001, Arizona Diamondback Mark Grace's home run total had a standardized z-score of negative 0.48. Interpret this value and then calculate the number of home runs he did hit. So 2001, again, we're using 2001 because we have our mean and standard deviation from that year. So 2001, we know the mean and standard deviation, so we can use that. So what that means is that Mark Grace was 0.48 standard deviations. Sorry, I'm changing my abbreviations out. Standard deviation, we'll see this was below the mean. So I'm not using the negative symbol. I'm just saying above or below. So if I want to calculate, I know, so I'm going to use my formula, right? Z equals X minus X bar over the standard deviation. I'm using some symbols there that are words. So we know the z-score was negative 0.48. I am looking for X. I know the mean that year. The mean was 21.4. And the standard deviation was 13.2. So if I use algebra, if I cross multiply, negative 0.48 times 13.2 is equal to X minus 21.4. So I would add 21.4 to both sides. And I would end up with X is about 15. So again, I'm going to round that to a whole number because he can't hit part of a home run. So calculate the number of hits. So he scored about 15 home runs that year. So again, that is below the average of 21.4. Okay, and let's talk about transforming data and density curves. So what is the effect of adding or subtracting a constant from each observation? So let's say my data is 0, 1, and 2. Keep it super simple. So what is my mean? So this is my center. And what is my spread? Well, my spread is 2. 2 minus 0. So what happens if I add 5 to every number? So 0 is now 5, 1 is now 6, 2 is now 7. So my center has changed. And how has it changed? It's changed by adding 5. What happened to my spread? My spread is still 7 minus 5. My spread is still 2. So what is the effect of adding or subtracting a constant? It will change the center, but not shape or spread. So if I had a little graph of it, so let's say I have a distribution that is normally distributed like that. What happens to it when I move it over? Like if I add 5, it's now here, but I haven't changed its shape and I haven't changed its spread. I just moved it to the right. Wish I had a different color for that. Okay, so what happens when you multiply or divide? Let's keep our 0, 1, and 2 again. So again, our spread is 2 and our center is 1. Let's say I multiply everything by 3. Well, 3 times 0 is still 0, 3 times 1 is now 3, 3 times 2 is now 6. Did my center change? Yes, it did. It was also multiplied by 3. Did my spread change? Yes, it did. My spread is now 6, which again is 3 times bigger than my original spread. So the effect it will change the center and the spread. But will not change shape. So if something is, so again, let's say this is my 0, 1, and 2, and that is approximately symmetric. What happens when I multiplied by 3 is I just made it wider. So now my new distribution might look like that. So I made it taller and wider, but I did not change the shape of it. Okay, so in 2010, taxis in New York charged $2.50 just to get in the cab, and then $2 a mile. So the fare that you spend is $2.50 plus 2 times however many miles you travel. So at the end of the month, the businessman collects all his receipts and analyzes the distribution of fares. The distribution was skewed to the right with a mean of $15.45 and a standard deviation of $10.20. So what are the mean and standard deviation of the lengths of his cab rides in miles? So solving for miles, so if I worked backwards and solved this for miles, what did I do? I would have subtracted 250 from both sides. And I would have divided by 2. So in this case, if I take my mean of 1545 minus the 250 and divide it by 2, I get my miles is 6.475 miles. Because when I am looking for my new center, I'm going to do the addition and the multiplication, because that's my center. But for standard deviation, my standard deviation of 10.20, I'm only going to do the division of 2. I'm not going to subtract the 250 because standard deviation is a measure of spread. So miles is going to be the center. And spread. And this, we will just do we will do both the addition and the multiplication affects that one, but here, standard deviation, only the multiplication. So I'm only going to do the dividing by 2 part. So my new standard deviation would be $5.10. So the mean length of a cab ride is 6.475 miles with a standard deviation of, whoops, why did I put that in money? With a standard deviation of 5.1 miles. Okay, so if the businessman standardized all of the fares, what would be the shape, center, and spread of the distribution? So the shape stays the same. In other words, it was skewed to the right. And then what is our center? So if our center, if we subtract 1545 from each data value, the mean will be 0. And then our spread, so all I'm doing there to get that is doing 1545 minus 1545 divided by 2 gives me 0. The spread would be taking the 1020 and dividing by the 1020 and getting 1. So that's what we're dealing with. When we're dealing with our normal distribution, we're looking for a unimodal bell-shaped curve. Our center is going to be 0, and we're going to go 1, 2, 3 standard deviations above, and 1, 2, 3 standard deviations below. So these are the z-scores of a normal distribution. So the z-scores, so one way to abbreviate that, we do n for normal, and then this is the mean, and this is the standard deviation. So every standardized normal distribution has a center of 0 and a standard deviation of 1. So that's how it is standardized. They're always the same. So what is a density curve? This is an example of a density curve. We have a horizontal axis, and the area underneath it is 1, because we're going to start shading parts of this, and we're going to figure out what percent of that is shaded. So histograms are also examples of density curves. The area under each one of those bars added up is 1. So again, normal curve I just introduced. We will use it throughout much of the year, and we will be finding the percent that represents what observations we're interested. So we'll do some of that very shortly. So again, how can you identify the mean and median of a density curve? Well, if it's nice and normal, it's right in the center, the mean and median. But the median is the point that cuts it in half, so I would expect 50% to be shaded on the left and 50% to be shaded on the right. And the mean is a balancing point if the curve was made of solid material, so where you would put it to balance it, so that it wouldn't tip over. So if it's roughly symmetric, the mean and median are the same, and if the data is skewed right, the mean will be greater than the median. Data skewed left, mean will be less than the median. I believe we've talked about that before. So I could have a density curve that is uniform, and if I told you that this was 0, 1, and 2, you would have to know that this height only went up to 1/2, because the area underneath, if this is 2 units wide by half a unit tall, then I know that the area underneath is 1. So if I'm looking, so a density curve can be any shape, but the area underneath it is 1. So even if I had something that was like this, I could use my information about triangles so I could figure some stuff out, but the area underneath that is 1. So no matter what shape it is, the area underneath the density curve, this area, is 1. And that's it for today.